Hello, I'm Andrew Smith from the Open University, and in some ways, finally, we're going to get to what it's all about. We're going to look at Module 14 routing concepts, or how we move traffic across the internet, or how we learn what devices there are across an internetwork system. As ever, I am not going to waffle through this slide deck, and what you probably also noticed in some of the videos that I've done in the past is I've already given some brief demonstrations of routing protocols. Basically, a router has a job. It's just simply to move traffic from one network to another network. But to do that, it has to learn about what networks are available out there and where to find them. And that's called path determination. So it will know what the directly connected are, it will know what the adjacent networks are, but it needs to know what the afar networks are and how to move the traffic to them, out of which interface and where and what direction to send them. And we do that using the routing table, which will then inform our path determination accordingly. But the routing table can either be configured statically, using static routes cunningly, or can be configured using a range of different routing protocols. And you may eventually learn that you can actually propagate information between routing protocols using a term called redistribution. So routing protocols can run separately and route separately across a common network fabric, or they can actually move traffic between them based on different rules, route maps, redistribution rules, access control lists, filters, and so on. So we can actually do all sorts of clever things at a much more advanced level. The best path is usually the best match, and it's about working out which route we're actually going to sort of send the traffic on, and it is based on a longest match binary principle, whether it's IPv4 or IPv6, and it's all about matching which path and which subnet and which network we're likely to have. But you'll also learn with the path determination where are we going to, then it's also about the best cost route as well. Is it directly connected? Is it remote? Has a default route got precedence over a learned route? Well, actually, a directly connected should win over a remote network, and then a remote network that's dynamically learned should win over a static route. But we can actually configure our routing protocols and our administrative distances based on whatever our local need is. So some protocols work better than others, learn faster than others, and obviously the challenge with default routes and static routes is if the connection goes down, it doesn't mean it's going to know about it. There is no updates taking place, whereas a routing protocol, updates are always taking place and interfaces are up and down. And with a directly connected network, if we can't see it, it ain't directly connected, so it ain't on, isn't on, or the cable isn't plugged in. And that gives then us, or the route of the job, of doing packet forwarding based on the prefix, based on the best forwarding decision, based on the best possible network, with the shortest amount of hops, or the best administrative distance accordingly. Okay, and then that way we will either forward it between directly connected, which Cisco routers do automatically, and they will re-encapsulate the Ethernet frame with the new information. So the source and destination MAC addresses will become the source and destination ports on the router and the remote device. So it is passing on that layer 2 and it's stripping off that layer 2 information, but it's keeping the layer 3 IP and routed information and passing that on to the next hop. And there's a whole series of great videos in the curriculum that demonstrate how this operates. But basically, it's like a pass the parcel game, but sometimes we actually have to add another wrapper onto the parcel based on who it's going to go to next. And at layer 2, the MAC addresses stay within the LAN segment. And at layer 3, the IP addresses remain relevant according to what hops is being passed through from the source and destination network. But if we don't know where it's going, we can't find the destination network, we will drop the packet. And that's where we get the destination unreachable or no reply, especially if we're using ICMP or pings. And that way, the aim is to ensure that we've got end-to-end packet forwarding operating here. And actually, Cisco here are actually talking about two older legacy serial technologies. But basically, for a routed network, you have to ensure that it's being encapsulated in the format according to the medium or media it's being transmitted on, irrespective of platform, whether it's wireless, copper, or fiber. Now, there are different packet forward mechanisms. There's two open standards, and obviously Cisco always has their own as well to run for higher performance within their own infrastructure. Process switching is very much an older method which pushes through the control plane of the device. Fast switching now, it's pushed through, and there is ingress and egress ports just checking where the first packet is going and then pushing the rest through, basically on the fast forward cache. There's a little bit of initial decision making, and then it's just basically passed straight through until obviously errors occur, and then express forwarding will actually build up what's called an adjacency table or the forwarding information base. So there's a little bit cost of learning, but then it's passed straight through, which reduces CPU time, and it's all done on the data plane of the routing device. We're going to look at a basic router configuration. With a little bit of a legacy network, you're not going to see many serial connections nowadays, if at all. But this is a great example of some ports that are being set up on a router. Obviously, we've got the standard configuration. Then we bring up the interfaces. Routing won't happen unless an interface is up. Okay, no interfacey uppy, no routy protocol. Okay, might seem quite trivial, but that's quite important. And to check, start off with IP root, but also look at IP interface brief before looking at any other of the verification commands. You've seen all of these before: show run, show interfaces, show IP interface, and obviously ping and trace route as well. And you can see this is a little bit of a repeat side. You can actually filter the output, especially of a run, to see how you've configured the system. And I would do this packet tracer activity so you could actually look at IP routing table. It will show the directly connected, it will show what it's learned by static routes, and it will show what it's learned by dynamic routing protocols. And it will also show if it knows about a potential default route, a candidate. That means it is possible that you may be able to send traffic this way. Not guaranteed, it just means it's possible. Because obviously if you do a wrong ping or send the wrong traffic to the wrong network, and it's just going to go, I don't know it, I can't read it. Because it tries the next hop. The next hop doesn't know about it, nothing is going to come back. So it is very much a best effort methodology. Every router makes its own decision, but it will make a decision based on the routing table, and it will make a decision based on the best possible path it can make. So it will find out where it's learned information from, what the destination is, what the administrative distance is, the metric, the next hop, the timestamp when it's learned, and the exit interface. And all of those values are used in routing algorithms, which means that you can actually have networks that have been learned by multiple interfaces, and then it will make a decision which is the best route or the fastest possible route that you can take to a distant network based on the fact I know where it is via 3 different destinations. However, understanding that means that if a interface goes down, it will be able to reroute traffic and do equal cost load balancing. EIGRP will actually handle unequal cost load balancing, which I think gets mentioned in a future slide. Directly connected, then it will immediately send it through the router straight down to the locally configured interface. Obviously, a static route, there are no routing overheads, there is no cost. However, they are not necessarily a stable routing methodology. So obviously by the end of CCNA to SRWE, you are going to learn about static routing, even though we're going to show you an example after the couple of this slide presentation and the next slide presentation, where I'm actually going to build a redistributed static routed network and show you the sort of traffic that moves around the system. And I'm actually going to create something using multi-area OSPF. Okay, also with static routes, we'll know the direct connection, we'll know the next hop, and we'll know the network and the subnet mask accordingly. And the important thing is if a next hop is an IP address, it will route through the interface that knows about it. If it does it on a port ID, it will rely on that port being up. Whereas also a next hop of an IP address could be different ports, whereas a physical port, the ports could be up or down. Pros and cons to either. One dynamically will try different ports. The other one securely will rely on that connection being up. So you, as a network administrator, will have to decide which is the best possible configuration to work for your system. Dynamic protocols will learn and will relearn and will learn on the best cost updates happening between the hello packets on our networking infrastructure, which means that we will then see dynamic routes. And in this example here, you can see it's telling us that it can actually see these two networks via 2 different interfaces or to our 2 different IP addresses as well. And that's quite useful, so we can see different IP addresses it's learned from or different interfaces remotely, which builds up quite an interesting table. The default route is always the gateway of last resort, and it means if I know nothing else, I try here in the hope that something might know about it upstream on the next hop. The routing table will always have what is effectively the next hop addresses or the child routes and the possible different connections that we can make outside the system. And it's always, yes, as I say, it's the possible available based on what it has possibly learned, because sometimes the routing protocol will know about a future network, but it's gone down, it hasn't relearned the change in the topology yet. Which is why we have different administrative distances on the network and what is a better value or more trusted protocol than another. So obviously the higher the administrative distance, the lower the trust of the protocol is. So directly connected, we will trust it. A static route, we will trust it, even though there's no cost and it could be flaky. And then obviously EIGRP summarized routes are more trusted than an internal EIGRP summary route. And then you'll learn about the different sort of protocols and how they trust accordingly. Ideally, you shouldn't be using RIP. It is legacy, and external EIGRP is rarely used. and internal BGP is really easy. It tends to be external BGP will have a better cost metric than over an internal route, and OSPF is lower performing than internal EIGRP because obviously it's Cisco proprietary. But whilst static routes have a better administrative distance, they have a lower trust in so much as if you screwed up your config, it ain't going to learn. It isn't going to learn across the system. That's why you have to decide what you're going to use. Are you going to use static or dynamic or both? And the answer is always both. Dynamic routing is flexible. It changes according to topological issues or opportunities, and will grow according to the system, so it's easier to administer. But when you've got stub networks, which are networks that go off on branches, sometimes the static route is the best, because then you don't have to have a high configuration overhead, and you don't even need to have insecure updates propagating between the stub and the local system. So you decide accordingly how you want to configure it for your environment. And dynamic routing will always scale. You can keep adding to the edge. With static routing, you've got to keep configuring, keep configuring, keep configuring. And this sort of slide gives a good example of what goes on. There's very little resource usage. Security is inherent only because there is no updates, but it is better for simpler topologies and requires more overhead, whereas dynamic routing, obviously you're going to have to set up authentication, like MD5 authentication, which you will learn on EDSA with OSPF, but you've now got a system that will change according to the structure. A little bit of a detour. We're going to just talk about the evolution of routing, and you can actually see how sort of protocols started developing since the 1980s. Obviously, some legacy going back into the late 60s, early 70s. And this is a great sort of exploration of how the internet evolved. So when some people say the internet is 40 years old. Well, it's correct on this slide, but of course there were predating technologies in the 70s and late 60s as well. So I am almost as old as the internet, as some will say. But what's quite interesting is how the evolution has taken place. RIP is legacy. I know some people still use RIP, RIP v2 and RIP v1. It is legacy. Even RIP at next generation is legacy. You should be using dynamic protocols like ISIS, intermediate system to intermediate system, EIGRP or OSPF, whether it's for IPv6 or IPv4. And obviously BGP is being used to run the external internet. So obviously BGP and BGPMP are the sort of protocols that actually run the external internet accordingly. And here's a good example of the kind of ones you'll use. And some are distance vector and some are link state. Obviously distance vector is about hops and paths and routes, and link state is about connection, and it's actually using a variation of Distran's algorithm. What people don't point out is the IGRP is technically hybrid, where it uses a combination of a distance vector and link state in its behavior using a diffuse update algorithm. But obviously you're going to look up how finite state machines work. And those of you that know anything about those, you're very fortunate people. Okay, so routing protocol is focused on the discovery of remote network, always keeping themselves up to date, choosing the best path, and the ability to find a new best path if one occurs. Okay, so it can change, and it should change whether there's a loss or a gain within the system. And each routing protocol uses different messages like hello updates or multicast updates, and they will actually all run on different algorithms, hence why I mentioned a finite state machine. And their role is to determine the best possible path to a destination and then load balance the traffic accordingly. Obviously, most do it equally. EIGRP can actually handle unequal, so if you have two different connections to two different bandwidths, you can actually set it up. And there is something called the bandwidth command to inform the protocol what speed the connection is and get that bandwidth. You can actually watch it using some debug where it will go 1, 2, 3, 1, 2, 3 across the different connections as well. So I have covered a great deal here in the last 20 minutes, and I think it'll be a great activity once I've done another slide deck for chapter 15, where it's actually got some configuration examples, where I will actually build a redistributed static and dynamic network. I know that is way beyond the curriculum, but here at least you will actually see some of the pleasures that are routing protocols at this level. So thank you very much. I've been Andrew Smith from the Open University.